Hi everyone, my name is Neha Kardam and this is the 11th lecture on electronic communications. This lecture is based on antennas and wave propagation, and this is the part 1 of that lecture. In this lecture we're going to learn about different antennas. So let's get started. Antennas are the crucial part of any wireless system. They convert the transmitter's power output to electromagnetic energy, which can flow freely through space. And at receiver, the antennas convert electromagnetic energy back into an electrical energy. So these transmitter and receiver, they are basically they behave as a transducer, and you know that the function of transducer is to convert one form of energy into another, and that's what this transmitter and receiver are doing. Transmitter is converting the energy from electrical energy into the electromagnetic energy, and receiver is doing reverse of that. Now we are going to see quickly all these points which are mentioned here. Antennas comes in many different forms. Most are based on the principle of Hertz dipole. So we are going to see the Hertz dipole antenna in this lecture. Transmitting antennas radiate three fields: induction field, electric field, and magnetic field. Induction field becomes insignificant in size beyond a few wavelengths away from the antenna. So that's why we will mainly focus on electric field and magnetic field in all the antennas which we are going to study. The ideal theoretical antennas against which all others are compared is called isotropic radiator. And next is the radiation pattern of an antenna, which shows how well it radiates energy in three-dimension space. And then next is waves from the antennas may propagate by direction, line of sight, ground wave, and ionospheric refraction. And above high frequency, ionospheric propagation becomes rare. A link budget is used to quantify the performance of a complete transmission system, including transmitter, receiver, antennas, and the surrounding environment. So this wave propagation we are going to cover in the second part of this lecture, and in this lecture we are mainly going to focus on the antennas, different types of antennas, and the principle related to that. Now here we have electromagnetic energy, and the picture you see here basically represents the electromagnetic wave in space, and this represents the wavelength. Wavelength of an electromagnetic wave is basically the distance that the wave travels in one cycle. And this electromagnetic wave, it consists of electric and magnetic field. And electric field lines, they are represented by this red color, and magnetic field lines are represented by this greenish blue color. And the electric field lines, they are vertically up and down. You can see here their orientation, whereas the magnetic field lines, they are in horizontal way. First direction is shown here and the other direction is like this. You know that how this wave is built up. This wave is built up when in a transmitter electrical energy converts into electromagnetic energy, and that electromagnetic waves moves away from the antenna at a speed of light, and that electromagnetic wave is actually shown here for one cycle. Let's read here. A radio wave is electromagnetic energy which travels at a speed of light. It is calculated by this formula, where this lambda is the wavelength and it is equals to this v, and this represents the speed of light, and f is the frequency. A practical transmitting antenna needs to be at least 1/4 of a wavelength to work efficiently in general. What is the wavelength of a 1 kHz audio signal, and why is this a problem? So here the frequency is given 1 kHz, and we have to calculate the wavelength. So what we'll do, we'll put the value of this frequency 1 kHz over here, and then we will put the value of speed of light, which is 3 × 10⁸ meter per second. And when you do the math, then you will get 300 kilometers, and that will be the wavelength. So the wavelength for 1 kilohertz frequency, it's going to be ultra long wave, and that type of wave is mainly used for submarine communications. And this 1 kilohertz is actually not visible to people, and it's mainly lies under the audio range, and you can hear it if you connect it to a suitable earpiece or a loudspeaker. Now here in radio wave, we also need to know the polarization. So polarization is mainly refers to the orientation of the electric field component, and the polarization of the radio wave, it is divided into two parts: vertical polarization and the horizontal polarization. In vertical polarization, electric field goes up and down with respect to the earth, whereas in horizontal polarization, the electric field is in the horizontal direction, and the magnetic field is going to be vertical. So in general, if you want to achieve the best performance, then the polarization of the transmitter and the antenna and the receiver's antenna, they should match in order to get the best performance. And there's another type of polarization which is called the circular polarization, and it is often used in satellites communication because of the relative orientation of the receiver and the transmitter, and it is hard to control. So that's why circular polarization is much better in those kind of applications. And when the electromagnetic energy, when it travels from the transmitter to the receiver, and you know that they have these polarizations, and these polarization can be changed in many ways. They can be affected by reflection, and that reflection can happen through anything. For example, like your buildings or other obstruction can alter the polarization drastically. And if a polarization is changed, then that effect is called your Faraday rotation, and it is strongly affects the radio wave in the high frequency range from 3 to 30 megahertz. Now next is the isotropic antennas, and in this, if you want to calculate and compare the performance of various antennas, then we often compare them with the isotropic antennas. However, such type of antennas actually don't exist, but the idea is that isotropic antennas, they radiates equally in all the directions, so their height, width and depth, they are going to be the same. So isotropic antenna is often used as a basic for calculation of field strength, and you can see here the top view and the side view of isotropic antennas. And here it is important to note that antenna gain is different than the amplifier gain. Antennas do not have a power source that allows the antenna to create additional energy to boost the signal. Antenna gain is actually measured, it is a measure of the amount of focus that an antenna can apply to the incoming signal relative to one of two reference dispersion patterns. And all antenna gains, they are actually specified in dBi. So dBi is actually the amount of focus applied by an antenna with respect to an isotropic antenna, or we can say with respect to isotropic radiator. And isotropic antennas, you already know that they radiates the energy equally in all the directions. Now next is the isotropic antenna. Here is continued, and in this we have electric fields intensity, magnetic field strength. Here on the picture, this square box which you see, it is actually a wavefront from a isotropic point source, and with the appropriate equipment we can measure the electric and magnetic field strength or intensities of a radio wave. On the left side, this electric field intensity, its meaning is how strongly the difference in potential between 2 points are in space, and as the distance between the point source increases, which means this d is increases, then the electric field intensity, it will decrease, because they have a inversely relationship. And here this PT you see here, it is isotropic radiated power, and d is the distance from the point source. And the formula for magnetic field strength is also given here, and it is under root PT by 68.8 D, and again the PT is the isotropic radiated power. The unit for electric field intensity is volts per meter, whereas for magnetic field strength it is in amperes per meter. Now next is the power density and characteristics impedance. And it states the power density of a radio wave. It is the amount of power that is distributed over an area, and it is calculated by this formula, which is based on Ohm's law. P is equals to EH. E you already know, it is the electric field intensity, and H is the magnetic field strength. And if we put the values of these two quantities over here, then we will get the final result as this, which is PT by 4 pi d square, and the unit of this power will be in watts per square meter, as you can see, because of this d square. So this power density, actually it falls off as the square of distance, and this is the one reason why so much of amplification has to be performed in radio transmitter and receivers. And this is sometimes also referred to as inverse square law of power. Now next, here we have characteristics impedance, and it is given by this formula: Z is equals to E by H, and where Z is the impedance of a medium, for example like in space. If you talk about transmission line, it needs to see a matched load at its end in order to transfer 100% of its energy and avoid any kind of reflection. Antennas should function as an impedance matching device. The antenna accepts the traveling radio frequency wave from the feed line. It performs the necessary impedance transformation so that the wave can continue to flow out into space with 100% of its energy. Now here we see the one of the antenna, which is the Hertz dipole antenna, and it is the simplest and most popular type of antenna in communication system. If you see here, it consists of two conductors, this and the second one is this, and they are 180 degree out of phase from each other. And these two conductors, they could be made up of wires, rod, or tubing, and they are 1/4 wavelength long at the operating resonant frequency, and each half of the dipole presents an identical impedance, and therefore the total impedance of a half wave dipole is just twice that of each side. And when many wavefront basically they passes down the antenna, then the voltage standing wave pattern will be developed. I hope you remember we saw the standing wave voltage standing wave pattern in the last lecture. So that will be developed over here when multiple wavefronts will be passed. Now here you see the voltage and the current pattern. At the feed point, the current is higher and voltage is lower, whereas the voltage at the dipole side is higher and the current is lower. The same is here. So we see that in the end of the dipole, they will relatively have a high impedance point, and that is why we see the higher voltage here at the dipole side. Now in this, if you use the coaxial cable, then it will use around 75 ohm of impedance, which is actually excellent, which provides excellent match. When I say match, it means the radiation resistance of the antenna must be equal to the characteristic impedance. And when they both are equal, then the standing wave ratio is minimum, and maximum power will be achieved in the antenna. And now let's talk about these conductors. So if the conductor's thickness, if it is increased with respect to the length of the antenna, then the radiation resistance of the antenna, it will decrease. And a typical length to diameter ratio for the Hertz dipole antenna is around 10,000 for a wire antenna, and the radiation resistance will be about 65 ohm. And here on the right hand side, you see how the Hertz dipole antenna is connected. This is the feeder line, and this is how it is connected. And at the center you see insulator, and further it is connected at the dipole side to the insulator, and you can see 1/4 wavelength on each side. And here is the practical picture of Hertz dipole antenna, and they in total produce 1/2 of wavelength. Now next is the Hertz dipole radiation pattern. Radiation pattern, it is the 3D distribution of energy leaving the device. The 3D radiation pattern of an isotropic source can be thought of as a perfect sphere, where radio frequency energy is spread evenly over the entire area of the sphere in order to form equal signal in all the direction. Here on the slide you see the picture of the radiation pattern for Hertz dipole antenna, and each circle you see here, they represents a 1 dB change in the field strength, and the radial lines you see, they indicates the angle at which the power changes are measured. And this is the top view of the radiation pattern you see here, and this is the side view of the radiation pattern. In the top view, it radiates best from the side, if you see here, at 0 degree, and at 180 degree marks it radiates the best, whereas at 270 degree and the 90 degree it is not radiating that much. And this is because very little current flows to the end of the dipole, and that's why we see the maximum radiation here and not on these angles. Now here you see this is called as a major lobe, and major lobe is the area of strongest radiation from an antenna. And here you see the side view, and it shows the dipole radiation equally going in all the direction. And on the right hand side here you see another representation of these radiation. So you see this is the dipole antenna represented in XYZ axis, and this is the wavelength, total wavelength λ/2, and the representation of the radiation pattern is this z-axis and y-axis. With respect to this, you can see this how it will look like for the top view, and for the side view this will be the look. And this radiation pattern is also shown over here. This is how it will look like. Now here you see, if we come back to this picture again, the top view, we see this beam width. So we need to define what it is. So this beam width, it is the angle between the two 3 dB points, and 3 dB point they are measured with respect to maximum radiation strength in the major lobe. And half wave dipole has a beam width of around 78 degree. the beam width looks like a directional. It is actually a directional focusing in one direction, but it is not very effective. And if you are targeting a signal at a radio signal at a remote location, then this is not going to be very effective. So in conclusion, we can say that narrow the beam width, larger the gain of the antenna will be. And if the gain of the antenna will be high, then it focuses its energy over a narrow angle, which helps to eliminate any kind of interference, and we would be able to achieve to a target position where we want to send the signal. Now here the gain for the dipole antenna in dBi is 2.15, and beam width we have already explained. Now moving on to the next slide. Now next we have a Macroni antenna, and it is also called monopole antenna. A Macroni or monopole antenna is a 1/4 length radiator placed vertically over the earth, and the earth ground here you see provides return path for the radio frequency currents that flows in the antenna. So here you see this another picture which shows the return current flowing through the ground. This green arrow shows the return current, and this the red ones, they show the current flowing in the antenna. So this type of antenna, unlike the dipole, is an unbalanced antenna and should be fed directly with the coaxial cable. The shield of the coaxial cable is connected to the ground at the base of the antenna, and the center lead of the coaxial cable is connected to the vertical radiator. And because the ground under a vertical vertical antenna is actually a part of the antenna, it is necessary that the ground losses must be minimized. And to minimize the losses, the electrical conductivity of the ground must be made as high as possible, or we can have artificial low loss ground that also provide the high electrical conductivity. Now here on the right hand side we see the top view of a radiation pattern, and this radiation patterns, they looks like an omnidirection. They have equal intensity in all the direction, whereas the side view will look like this, and these are its major lobes. So this type of antenna, it is used for low frequency application, and this is the advantage. This is actually the advantages over dipole, and it only needs half of the dipole length, which greatly reduce the cost of this type of antenna. And the feed point for this antenna has a low impedance, and this type of antenna has some disadvantages also. And one of the disadvantages that the gain of this antenna is about 1 dB. The gain of this antenna is about 1 dB less than the dipole one, and this type of antenna is extremely dependent upon the conductivity of the earth, because earth acts as a mirror, and we need to increase the conductivity of the earth. And the earth conductivity can be improved, as I told you, by some artificial low loss ground, or we can also use the radial system. Radial system improves the conductivity of the earth, and it should be laid out in a pattern that follows the ground current that is running radially out from the feed point of the antenna. Now next we have Yogi Ada antenna, and this type of antenna consists of a driven element, usually dipole antenna, that is your driven element, and some extra antenna elements which are called parasitic elements, and those parasitic elements basically helps to focus the antenna's radio frequency energy in the forward direction. And those parasitic antennas are basically our reflectors and the multiple directors. So we see these two are basically parasitic elements, and this is the driven element, which is our dipole antenna. And with the help of these we can basically make the Yagi-Yada antenna. Here also in this picture we can see the reflectors. This is the reflector and this is the director used, and this is at the center is the driven element. So here when the radio frequency energy is applied to the driven element, this center one is the driven element, then the energy flows outward and excites the parasitic elements, our reflector and the directors. So this reflector, it is made you can see that it is made electrically long. 5% it is longer than the driven element, and it serves to reverse the direction of the radio frequency energy and emitted back from the driven element. And the director element are in the front of the antenna, and they are made electrically short, 5% shorter than the driven element. These director element further reinforce and they focus the energy leaving the front of the antenna, and adding more directional elements in the Yagi-Yada antenna will basically increase the effectiveness of this antenna. In general, increasing these parasitic elements, the gain of the antenna can be increased. And this Yagi-Yada antenna, it is normally built for operation on a single band, and it can be made to resonate at different frequency, and that is why this Yagi-Yada is not considered a wideband antenna. Here on the radiation pattern you see the major lobe. This represents the major lobe at the front, and the minor lobe is basically at the rear. And here these two small lobes you see, these they represent the parasitic lobes. And this is the side view of the radiation pattern. And this type of antenna is mainly used in the television broadcast reception, where a wide frequency range must be covered. And the gain of Yagi-Yada antenna is around 7.1 dBi, which is very high compared to the other antennas we saw. Now next is log periodic antenna. So in this log periodic antenna, all the elements are driven by the feed line. You can see here they are connected, and even other elements in this antenna, they are connected 180 degree out of phase. The longest element L1 you see here is cut to be resonate at a lowest operating frequency, and the shortest element resonates at a highest frequency. And this antenna covers a large bandwidth without frequency break, and the directionality in this antenna is obtained as similar to the Yagi-Yada. Here you see this L1 reflector, and all the shorter elements, they all act as a director elements, and they have a ratio. This ratio is basically between two adjacent element, L2 and L1, and this ratio is similar to the above one, and it shows the spacing between the elements D2 and D1, which you can see here. This is D2 is the spacing between these two elements, and D1 is the spacing between these two elements. So these are the two ratios which can be obtained in this type of antenna. When compared with Yogi Adda, this one has multiple elements, directional elements you can see here. And the primary advantage of this antenna is that it can have a higher bandwidth, and it's operate on a wide band of frequencies. It can work for high frequency and ultra high frequency, and it also has a low standing wave ratio. Now next is the summary, and I'm going to quickly read these points. First, it says antennas are a crucial part of any wireless system, which is true. Polarization refers to the orientation of the electric field of a radio wave. Waves can be vertically, horizontally, or circularly polarized. Receiver transmitter antenna polarization must agree for best signal transfer. The simplest antenna is the dipole. It is somewhat directional and must be 1/2 wavelength long in its ideal form. The gain and beam width of an antenna are closely related. As the antenna becomes more directional, which is measured as a reduced beam width, its power gain increases. The Macaroni antenna is a 1/4 wave stub over a ground plane. When placed vertically, this antenna is omnidirectional. So all these points we have already covered in the lecture, and now is the end of the lecture. So thank you for watching.